Today we're going to be talking about Maclaurin series, which is just a way to write any function, no matter how complex, as an infinite sum of polynomials, and that infinite sum is defined on the top right. And we're going to see how to derive this formula. But first you may be wondering, why would I want to take any function, let's say sine of x, and write it as an infinite sum? Isn't that just a much more complicated version? Well, the reason is because computers find it much easier to calculate a polynomial rather than, for example, a trig function, right? When I plug in sine of 1 into a calculator, it can't just draw a right triangle and take the opposite over hypotenuse of an angle of 1 radian. It's actually going to use an approximation using this not infinite sum, but very large sum of polynomial terms, and plug in x equals 1, and that's the number you get out on your calculator. And you may have actually seen a very short example of a Maclaurin series in, for example, a physics class, where you may use, or engineering as well, where you may use the small angle approximation, which is simply defined to be sine x equals x. There's also small angle approximations for tan x and cosine x, but sine x equals x is a very famous example, and sometimes it's jokingly called the fundamental theorem of engineering, because engineers generally use approximations rather than exact values. And this has many applications outside of just computing sine of x in an easier way. For example, when you learn about diffraction, for example, single slit diffraction, the formula actually uses this sine of theta equals theta just to approximate it, because the angle theta is very small in these cases. Okay, so since we looked at sine of x for our examples of applications of Maclaurin series, now we can look at how to derive sine of x's Maclaurin series. So let's say we have a function sine of x, which looks like this. So f of x equals sine of x. And we want an infinite polynomial that is exactly the same as sine of x everywhere. So we can start off by writing this polynomial beneath as a plus bx plus cx squared dot dot dot, where we don't know the coefficients of each term. So we can start by saying, well, since it has to take on the exact same values of sine x everywhere, it must also have the same value of sine x at x equals 0. So, since we know f of 0 for sine x is 0, sine of 0, f of 0 must also be 0 for our infinite polynomial. Now, if we plug in 0 for x, all the terms with an x in it cancel, leaving our constant, which is a, which is 0. So we've satisfied one condition to make our function look slightly similar to sine of x. Now, if we want to get an even closer approximation, we can say that the rate of change, or the derivative of both functions, must be equal around x equals 0. So the rate of change of sine of x around x equals 0 is just the first derivative of sine x, which is cosine, and cosine of 0 is just 1. Now the first derivative of our function will just make the constant term go to 0, bx will become b, cx squared will become 2cx, and so on. Now, since we're plugging in x equals 0, once again, we're just doing everything around x equals 0, all the terms with an x will cancel to 0. So we have f prime of 0 is simply the constant coefficient b. And it must equal f prime of 0, which is 1. So now our second condition is fulfilled, where b equals 1. And we can simply continue this pattern by looking at the second derivative, because the rate of change of both functions must also be exactly the same. And f double prime of sine of x is just going to be negative sine of 0, which equals 0. So looking at our second derivative of our polynomial, it will simply become 2c plus 6dx squared, or 6dx actually, and it will just go on to infinity. But all of these terms after 2c are simply 0 when we plug in x equals 0. So if we want to satisfy this condition, 2c must equal 0, so c must be 0. And we can tell that all coefficients of any even-powered term, for example, x to the 0, x squared, x to the 4th, it will always be 0, because the derivatives of sine of x always alternate between some form of cosine of x and then sine of x. And every even derivative, for example, the second derivative, will have sine, and sine of 0 is always going to be 0. So we know that all these even powers are going to cancel out. But the odd powers are going to follow a pattern. Now, to notice this pattern, we can look at the third derivative, where the third derivative of x is simply 6d with a bunch of x terms, which will all go to 0. And the third derivative at 0, if we look back up here, third derivative of sine of x is simply negative cosine of 0, which is negative 1. So that means 6d must also equal negative 1. And then we have d equals negative 1 over 6. So we've satisfied a fourth condition, where now our polynomial looks much closer to sine of x, and we can actually see this by graphing in Desmos. And if you look back at the small angle approximation, we can actually see that it is simply the first term of sine of x's Maclaurin series, because this is just the bx term, where b equals 1. And this is actually a surprisingly good approximation. As you can see in our graph, all values close to 0 are very close to the line y equals x. Now, if we continue finding higher order derivatives for sine of x, we're going to get a closer and closer approximation using our polynomial. And as you can see on the denominator for d, we have 6, which is the same thing as 3 factorial. And we can see that comes about because the term was originally x cubed times d, and then it became 3 times d times x squared. And then once we took another derivative, it's 3 times 2 times d times x. And then taking another one, we simply have 3 times 2 times 1 times d, where 3 times 2 times 1 is simply 3 factorial. And we can see this pattern will happen with all higher order derivatives. For example, if we go to the fifth derivative, since the fourth one will essentially do nothing because sine of 0 will again be 0. If we go to the fifth derivative, we know that the term f times x to the fifth will go from f times x to the fifth to 5 times f times x to the fourth. And taking more and more derivatives, we'll leave 5 factorial times f as our coefficient. And we can also see that these terms b and then d and then f, all these odd coefficients will also alternate in sign, where they start off positive, then become negative. So if we want to find the complete formula for sine of x, we can just do a little bit of pattern recognition and see, since we know that they're going to alternate in sign, this is because the derivative of sine alternate in sign, we'll see that we have negative 1 to the n, and we can actually start our index at n equals 0. And then it's x to any odd power. Now all odd powers can be written as 2n plus 1. And as we saw earlier, we would have, for example, 5 factorial times f equals positive 1. Then the coefficient f will just be 1 over 5 factorial. So here in our infinite sum, we simply divide by the power, which is 2n plus 1 factorial. And this is actually the exact infinite sum, which equals, not just approximates, but equals sine of x everywhere. And we can see a visual representation of this in Desmos, derived alongside sine of x. Right now, our sum only has the first term, which is the small angle approximation. However, if I increase the amount of terms, our two functions become indistinguishable from each other. And with infinite terms, they actually become the exact same function. Now, this method for finding Maclaurin series can be used on any function, for example, e to the x or other trig functions, and can be used not only to simplify calculations for computers, but also possibly take the antiderivative of a non-integrable function, or take the derivative of a very complex function. And this is used in many engineering and physics applications. Thank you for watching.